at Cornell?
We try to get in person if possible. So about, I would say, more than half have been in person.
Yeah, it's roughly the same for us. Although, yeah, towards the end here now, most of them now back on Zoom.
Right.
And I got a feeling back in January, it's going to be back on Zoom again. Yeah.
Oh, so you are really worried about the
yeah, I think this one doesn't look too good. I was pretty optimistic until recently, but this one doesn't look good. Probably not a lot of people will die, but just the reaction of people and the uncertainty and yeah, I think.
But people are coming, so I mean, you are not the only in your office, right? I mean, that people are coming to the university.
Yeah. Everybody's coming to the university. I think that one is that part I don't think is going to change. I hope not, I hope universities are not going to be shut down. How much people travel, that's the part I'm more worried.
I see. Yeah. But people are lecturing with masks on, things like that, right? At Cornell.
I was lecturing with face shield, yeah.
Okay. With a face shield.
Like this.
Yeah, exactly. Yeah, no. You don't have to do it now, though.
No, I'm in my office alone. So.
The university allows you to take your mask off in your office, right? But once you step out.
Yeah.
Well,
usually also, I'm not sure whether it's legal or not, but when we have lunch, we would take off the masks. And I don't think we are supposed to do that, but they do that in the cafeterias anyways. So
yeah, same thing was happening here actually. So we got a reminder that we got to keep our masks on. People were taking their masks off longer than normal when they were eating. So yeah, we had
while you're eating, you'll have to.
Well, unless you have a straw with a hole in your mask. Anyway, I think then we can get started then. So it's a real pleasure today to have Csaba give a talk. Csaba got his PhD from MIT. And then after that, he had positions at Berkeley and Los Alamos before joining the faculty at Cornell in the early 2000s and has been there ever since. And Csaba, his work basically is across the field and beyond the standard model, from cosmological constant, supersymmetry, composite Higgs, cosmology, extra dimensions. He's basically worked in every area. And today we're very happy to have him, and he's going to tell us about his recent work on phases of gauge theories via AMSB.
Thank you very much. So it's great to be back, at least in spirit. I think one of my last seminars was in Minnesota. I think in the fall of 2019. Well, hopefully I can be back in person too at some point. So today I will be talking about the work that we have been doing over the maybe last half a year or so. And it's in collaboration with my student at Cornell, Andrew Gomes, and Hitoshi from Berkeley and from the IPMU in Japan, and my former student who is now postdoc in Berkeley, Ofri Telem. Okay, so let's start here. Okay, so here's the brief outline. I'll tell you, why, this kind of direction seems to be interesting. I'll give you a brief review of Seibergology, which is like exact results in 4D supersymmetric gauge theories and their uses, and also of anomaly mediation. And then I'm going to try to show you how to perturb Seibergology with anomaly mediation and get sort of novel kind of results, some of which are exact, in the non-supersymmetric theories as well. And, for example, we'll see, confinement in the SON case actually showing up. Okay, so let's get started. So one of the most interesting and important unsolved questions in particle physics is, to find what the vacuum of strongly coupled gauge theories are, like, nailing down the confinement mechanism in QCD, answer the type of questions like, for how many flavors do we actually expect chiral symmetry breaking? Does confinement persist for a large number of flavors? I mean, we know that there is at least one other phase that is probably realized in ordinary QCD as you increase the number of flavors, because very close to the regime, when you are losing asymptotic freedom, you can do a reliable perturbative calculation and establish that there is a conformal phase following the work of Banks and Zaks. So that's called Banks-Zaks fixed point. Now, not too many tools are actually available for studying this question. Obviously, the most powerful one is our lattice gauge theories. But for the case of chiral gauge theories, there isn't yet, as far as I understand, anything that is practically usable. There are methods, as far as I understand, that should in principle work, but they are still just too slow to give you practical results for the chiral cases. Of course, there is anomaly matching conditions. So those are one of our main friends. For the case of chiral gauge theories, there is a sort of a heuristic tool. I will be talking about that was discussed in the late 70s. The people called it Tumbling, and it's sort of like a cookbook recipe, to guess, what the vacuum would be. I will talk a little bit about that. And then, one of our biggest friends is, just try to extrapolate from supersymmetric gauge theories. So that's the direction that I will be focusing on in this talk. Okay, so let's try to understand what are the type of results that we know about QCD-like gauge theories that are supersymmetric. So SUSY is giving you very powerful constraints on the strong dynamics, and building, of course, on many other people's work. Of course, Misha and Arkady, did really important work on this prior, like in the 80s. Was it 80s or 70s? I don't remember anymore. Anyway, so of course it wasn't just Seiberg, but in his work, these results culminated in 1994 when he was basically able to give the phase structure of the supersymmetric versions of QCD. And the methods that he was using, the key, of course, was holomorphy. And then he also used Tuft anomaly matching. In some particular cases, you could do an instanton calculation. And then, of course, the methods of integrating out flavors and Hicksing the theory and flowing between the various theories was also giving you a powerful constraint that sort of eventually led to a web of results that all seem to be completely consistent. So this is the kind of theory that we are talking about. So this is a supersymmetric version of QCD. N equals 1 supersymmetry in 4 dimensions. So these are 4 supercharges, and they're assuming that there are F flavors of chiral superfields. So SUF cross SUF global flavor symmetry would be present. And in addition, there may or may not be U1 symmetries. Now, one of the really important results about the SUSY gauge theories is that there are so-called flat directions. They are often also called the moduli space of the theory. So those are directions along which there is no potential generated, and so those flat directions can be parameterized by the holomorphic gauge invariants. So in particular, for this SUSY QCD case, they are generically given by mesons. So those would be gauge invariants made out of a quark and an antiquark, or baryons that are like the nth power of the quark field or the conjugate of those. Okay, and the baryons are antisymmetric in the flavor indices. So they don't exist for a small number of flavors. So you need to have at least F equals n flavors in order for these baryons to exist. Okay, so So here is a quick overview of what the actual phases of supersymmetric QCD are. So as I said, it changes, the vacuum structure changes as you're changing the number of flavors. So I'm going to go quickly through it, but you see that there are all these different results. So for example, for the case of zero flavors, so that's the theory we would call pure super young Mills. Actually, what happens is there's gaugino condensation. So in this case, there is no continuous flavor symmetry, only a discrete flavor symmetry. There's a remnant of the R symmetry that is anomaly free. And what will happen here is that actually, due to the strong dynamics, there will be gaugino condensation that is happening. So there will be a gaugino condensate formed in the vacuum that's breaking this discrete flavor symmetry. And there will be a superpotential that is generated that is proportional to this gaugino condensate. And the theory should be truly confining because you don't have, so the phase, if you're asking what is the phase of this theory, because you don't have any massless dynamical quarks in the theory, the expectation is that this will be a truly confining one in the sense that the potential between the test charges will have this characteristic linear form. Okay, so that's the case when you don't have any flavors. Now, if you start putting in flavors into the theory, but not too many, so if you have more than, so if you have at least one flavor, but less than n, then actually what happens in these SUSY versions of QCD is that there will be a so-called Affleck-Dine-Seiberg superpotential generated, and it will lead to a so-called runaway vacuum. So ADS here doesn't stand for anti-de Sitter, it stands for Affleck, Dine, and Seiberg, so the D is capital. So this is actually something that was calculated not in 94, but quite a bit earlier, about 10 years earlier. And again, what will happen here is that there will be a dynamically generated non-perturbative superpotential present in the theory. And so it goes like 1 over determinant M. And these powers are actually relatively easy to fix by holomorphy and the global symmetries of the theory. And okay, so this is the superpotential that is supposedly generated. Now, in one particular case, when F is equal to n-1, you see that's the simplest case because you don't have this fractional power showing up here when n-F is exactly equal to 1. This ADS superpotential is actually generated by an instanton. So this is actually one of those cases where you have a weakly coupled instanton that is fully calculable. Okay, so this was done around the time. So people really have gone ahead and calculated the superpotential, including the coefficient for the case when F equals n-1. Here I just outlined here, the type of calculation that you have to perform. And then, of course, because they were able to establish the coefficient for n equals F equals n-1, so the coefficient was 1, then, of course, you could go down further and integrate out flavors and get the exact coefficient for the lower number of flavors. So the gauge group in this case, when you have this ADS superpotential is going to be Higgsed, depending on whether F equals n-1, then the gauge group is completely Higgsed. If it's less than n-1, then the gauge group is just partially Higgsed, and the remaining part is going to generate a gaugino condensate for you.
So I have a question. So this is why the calculation was able to be done because it was Higgsed, right? So
exactly.
The integral over the instanton size was cut off by this exponential.
Exactly. Cut off by the Higgs wave.
Yes. Okay. Yeah.
And the assumption was so the way you're supposed to do the calculation is you assume that the Higgs wave is very large. Mm-hmm. Yes. So that the theory is Higgs before the gauge theory becomes strongly coupled, and then you have a reliable instanton calculation, and then you check, is that then self-consistent? Yes. So you see that you get this superpotential that would like to actually push the wave to as large as possible. Yes. And so in fact that is a consistent approximation. Of course, now this superpotential, since it has 1 over the waves showing up, in fact would like to push the the meson wave all the way to infinity. Yes, so that's what it would be called a runaway superpotential. Yes, runaway direction. Yes. Now you can, of course, you can stabilize it if you add a little bit of a mass for the quarks. Yes, then you can actually stabilize this at a very large finite value, and supersymmetry would still not be broken there.
But still, this kind of notion of superpotential, whatever, in case where it's not kind of large Higgs field, not for f equal n-1, I would not say that it is clearly formulated, because it effectively it's a strong coupling becomes a strong coupling, right? So you cannot trust this calculation.
Well, so the calculation you won't be able to try, so there's no more instant-on calculation.
Sure, no, but moreover,
there's no, so we don't fully know what the mechanism for that, for the generation of that is, but it's the same gaugino so what happens is that then the leftover part of the gauge group, yes, that is not Higgs, is going to be a pure f equals 0 super Yang-Mills. Yes, and then that is going to generate a gaugino condensate. Okay, and then that gaugino condensate from the previous page, yes, this lambda cube, you can match it up to the theory with the larger number of flavors. And in fact, this ADS superpotential is literally the lambda cube of the low energy effective theory. Okay, but you do the matching in terms of the meson field. So in that sense, you would say that it is. So this result is sort of,
No, but it's not the same as to say that this particular dependence of potential of the field is correct. I agree. You see, your arguments are more, kind of more generic, and particular notion that you have the field in the fractional power. It does not mean that you can justify it. No, you can see it in particular example when you can have, like, say, two flavors, whatever. You can see that you are coming to the theory of some coupling when you are trying to go to the limit where those masses are small, and moreover, it depends on the ratio of masses. And I mean, you started from, say, the theory with, say, two light matter field. So what I'm trying just to say is that some caution should be taken when you are, kind of implying that, kind of when you are talking about runaway, I would not argue with this, right? But to say that this particular form of superpotential, I would argue that it's not proven.
Well, I mean, it is
an extrapolation. You are saying that if it's possible to write as a function of the field, then it would be this function. But the very fact that you can write it as this function is depends on certain details because you are in some coupling.
Well, again, I mean, the M is the is the modulus of the theory. Yes, you should.
Yes, that's true.
In terms of M, yes, and. So I mean, it's a self-consistent picture, yes, where you say, okay, let me try to ask the question, what happens to the theory if I turn on the meson waves, yes? I break part of the gauge group, the rest of the gauge group is unbroken, it generates a gaugino condensate, and that's the superpotential.
No, but now you are not sitting at large value of the field,
So if you are, so then you're asking what happens at the origin, yes? Well, we are saying the origin is really not allowed here, yes?
Okay.
The dynamics would like to push you away from the origin. That's what.
But I think that in this way you are losing. I mean, besides kind of more generic information, because say what you have a fractional power, right? Here, so you have like a branch cut in the dependence of field, and then. I'm asking you if it's a branch cut. Well, what means say kind of imaginary part?
This would tell you that you are just not allowed. You're not.
Yeah, I agree.
Sit close to the origin of the moduli space. Yeah. So
no, it's not the origin. No, when you have a square root of m or whatever fractional powers, an imaginary part is it's far from the origin as well. If you do analytical continuation of the field.
Imaginary part can be hidden in the definition of lambda because it can have a phase.
Right.
Globally means I agree. Yeah, but for global quantities, right? But here it is particular dependence, right? I mean,
but anyway, I mean, Arkady, I mean, this is not the, I think we sort of agree on, what we are saying. So let me just.
Okay. I'm sorry, but no, it's just to say that the clear notion of this is for the cases where there is no this kind of problem, right? For F equal, and for the other cases, it's a little bit symbolic.
Well, again, it's telling you the way I interpret it is that you're not supposed, the vacuum is not close to the origin, it's pushed away, and there, this is the superpotential that you're getting. That's how I would, interpret this. All right, so let me.
Can I ask a naive question?
Yes.
Sorry, it's still about this runaway vacuum. So, are quantum field theories where the runaway vacuum are really well defined? Like, does it make sense to discuss a theory?
The way you should interpret this is that you're adding a little bit, as I said, you're adding a little bit of stabilizing mass. Yes.
Well, okay, that's fine, but the massless theory itself, it sounds like, is somehow sick. Is that correct?
Well, you would say, it doesn't have a good ground state. Yeah, I would.
Right.
Okay. If you insist on the exactly massless theory, I would say it doesn't have a good ground state. Yes.
I see.
The supersymmetric version. And then, of course, what we would be interested in asking is what happens in the non-supersymmetric version when we, instead of perturbing it with a supersymmetric mass, we want to perturb it with a SUSY breaking mass. So that's
I see. Thank you.
one of the questions that we are trying to ask here. Okay, very good. So let me. I need to hurry up because I want to get to our results. So you can go through all of these Seiberg results for f equals n and n+1. There's some really simple description in that case. It turns out that in those cases, actually the origin is allowed or sort of allowed, depending on exactly whether f equals n. It turns out that there is the meson and the baryon themselves become the true degrees of freedom, true dynamical degrees of freedom close to the origin, except for f equals n. There's a quantum version of the classical constraint between the mesons and the baryons that you have to impose. Once you impose that, then you can check that all the 't Hooft anomalies are actually matched along that constraint. And for f equals n+1, so that's another special case. It's usually called the S-confining version of these theories. In that case, all the 't Hooft anomalies are matched by the meson and the baryon, and there's a dynamical superpotential for the meson and the baryon fields that will actually implement the classical constraints on these degrees of freedom. Now, what is the actual phase of these two special cases? So we usually call this a screened phase or a phase of complementarity. So sometimes people call it a confining phase, but the reason why we named it as confinement is to make sure that people understand that this is not actually a truly confining theory in the sense of if you're asking what is the potential between the external test charges, it's not going to be a linear potential. And the reason for that is that there are dynamical quarks in the theory, and they can actually screen all the possible external sources. And so what is nice about, for example, this S-confining theory is that if you go far out on the moduli space, you will completely break the gauge group, yes, and you can think of it as a Higgs theory. But if you go close to the origin, exact same theory with the same descriptions in terms of the same degrees of freedom will apply. But there you would interpret it more as one of these screened phases where you have these gauge invariants that you get out from the screening. So this is what is called the complementarity, where there is no phase boundary between what you call the Higgs and sort of confining theory, but better to call it.
But Csaba, I think that the major phenomenon which was demonstrated by Seiberg here, it's appearance of this kind of states, right? Which I mean, it's in certain sense, it's like, you know, existence of monopole in gauge series, in supersymmetric gauge series, but demonstrated in a different way.
You mean about the Seiberg duel?
Yeah, no, not just duality, just when you consider n and n plus one, I mean, this example, then you are proving that there are new states.
Well, yeah, so but those states, the M and the B, you know, you don't need to think of it, I think, in terms of monopoles. You can just
no, but it's
literally think of it as, you know, as
I'm not saying
invariants made out of your original degrees of
freedom. No, I agree, but monopoles are also made out of original degrees. So so it's another no, it's an I'm not saying that it's like that they are monopoles. I'm saying that it is example of appearance of
where you know, where you can identify what the true dynamical degrees of freedom of the theory are. They are massless.
In case of the only difference is that in case of monopole you have semi-classical example of monopoles constructed, and here do not have quasi-classical example. It is the only difference.
Right. All right. Let's go to the case when you actually have the so-called Seiberg duality. So when you keep increasing the number of flavors, then you are hitting two other type of phases. But there's one thing that is common about those, that both of those are going to be described in terms of the so-called Seiberg dual or magnetic dual. And so what Seiberg found was that if you consider your SUSY QCD, the theory that I outlined you that I would like to examine, then there is a corresponding magnetic theory in terms of a different gauge group, a magnetic gauge group, which is now given by SUF minus N. So the gauge group is going to be the number of flavors minus the number of colors of the original theory, but has, of course, the same global symmetries. As otherwise, you know, if you did, you know, the global symmetries are physical. So those you better have to match between these theories. And the claim was that these two theories describe flow to the same IR theory. So they describe the same low energy physics. And he had a lot of evidence for that. You could check the anomalies are matched between these two theories. They have the same flat directions. You can move up and down by integrating out, Higgsing the various gauge groups. Oh, and I forgot to say, in the magnetic theory, there's a superpotential. I forgot to add that there's an MQ bar superpotential present in the magnetic theory. Okay. And when the number of flavors is just above the S confining case, then the magnetic gauge group, this SUF minus N, is actually IR free itself. Okay, so in this range, the low energy effective theory will be that of free dual gluons, quarks, and mesons in the IR. Okay, so this is, you know, this was a pretty big shock, at least, you know, for people like me back in the 90s, because you know, you sort of saw an example of what I would call an emergent gauge symmetry, in the sense that, you know, you started out with the gauge theory in the UV, and in the IR you had a totally different gauge group. In some sense, you can think of them as a composite gauge group, and so you can play around with these, and you can actually, you know, if you live through the era of, you know, of compositeness as solutions to the hierarchy problem, you can mess around with these and build actual examples of, you know, a standard model where the W and the Z are actually partially composites using this mechanism of Seiberg duality. So it's a lot of fun. Now, if you keep increasing the number of flavors, at some point, of course, you know, the dual gauge group will will also become asymptotically free and not IR free. And there will be a range of flavors where both the electric and the magnetic theory are asymptotically free. So in that case, actually, Seiberg was arguing that the theory will be actually conformal. So both the electric and the magnetic theory are going to be flowing to the same infrared fixed point. Okay, and close to the edges of the of this conformal window, you can actually establish that there, you know, by perturbative calculation, that the theory is going to be conformal, because either the electric or the magnetic theory is going to have a Banks-Zaks fixed point, you know, just around the edges. So it is pretty plausible, and then you can have a lot of, you know, different consistency conditions that would tell you what what this fixed point is. In particular, you can calculate all the dimensions of the operators. You can calculate what the nature of the fixed point actually is. Okay, very good. So that's, and then of course at some point, the theory is just going to be IR free, so you lose asymptotic freedom. Okay, so this was the story from Seiberg a long time ago, 25 years ago or so. Yes, it's a beautiful picture, but it's very different than what you're getting from non-supersymmetric QCD. As far as we can see, lattice simulations only suggest two different phases for QCD. One of them is the one that we are used to, the one with chiral symmetry breaking, where SUF cross SUF is broken to the diagonal. And for a very large number of flavors, we don't exactly know how large. It could be perhaps as large as F greater than 3n. And of course, the boundary there is different, yes, because we are talking about non-supersymmetric QCD here. So F greater than 3n doesn't immediately imply loss of asymptotic freedom. There's at some point, there's going to be a conformal phase, because we know that there's a Banks-Zaks fixed point. So somewhere there's got to be a conformal phase. But those are the only ones that we have, as far as we know, any evidence for the non-supersymmetric theories. So we would like to start, making connections between the supersymmetric and the non-supersymmetric theories. And ideally, we would like to see, this kind of structure appearing when we perturb the supersymmetric theories. Okay, so we would like to add supersymmetry breaking. Now, we don't claim at all that we were the first to do this. There were, as soon as Seiberg's paper came out in '94, people have tried. Obviously, everybody understood that this is one of the most interesting questions. So a lot of work has been done on this. The first paper was by Aharoni, Sonnenschein, Peskin, and Yankielowicz. And so it was basically pretty ad hoc. They added soft supersymmetry breaking on the electric side, and then essentially just guessed, what will happen on the magnetic side. They assumed that there will be some corresponding soft supersymmetry breaking terms for the mesons and the baryons, but they assumed all of these are positive. So this was an interesting trial, but it was mostly guesses and not really based on some first principle matching of the SUSY breaking effects. Around the same time, there was the group back then. I guess they were all at BU, Nick Evans and collaborators. So they started to be more systematic. So they were trying to use spurions and holomorphy and broken global symmetries to restrict the allowed SUSY breaking terms. And so they did analysis for several different cases. But for example, for the ADS case, they still found a runaway direction, which is not quite what we think right now is the right answer. Now, an even more systematic approach was initiated by Xinxia Chang and Yael Shadmi. So they tried to now really truly find the mapping of supersymmetry breaking from the electric theory to the magnetic theory by sort of turning this whole, both the electric and the magnetic theory into a gauge-mediated model. So they added some extra massive quark flavor to both the electric and the magnetic theory, and they coupled that directly to supersymmetry breaking. So they assumed there's a SUSY breaking spurion X, and then they did sort of the mapping of the invariants in those theories. So essentially, they said that this will look like a messenger in the UV theory, and then you can just calculate the effects of SUSY breaking from RG evolution in the IR theories. Okay, so the results that they found actually were quite interesting. For the free magnetic theory, it was kind of disappointing because they found that there is a runaway direction either in the squark or in the meson field. So it looked like you won't have a good vacuum in these theories that they were investigating. And again, the SUSY breaking pattern wasn't at all like as expected in QCD. So, even if this was sort of the correct, phase of the theory, you would expect a phase transition to happen when you increase the scale of supersymmetry breaking. So,
yeah, but Csaba, when supersymmetry is broken, and they have non-zero masses, those direction could be kind of limited. Runaway could be stopped by non-zero masses, or it's not the case in this. Yeah, you see, because before, when it was runaway, it was about masses limit, right?
Right. So I think I thought this was a true runaway, but I think it can be probably, with the supersymmetric mass, if it's the squarks, for example, that get a negative mass squared, you can just add a large enough quark mass to stabilize it, I think. But we really were trying to understand, what's the theory at the origin. Yes. So all right, let me go back here. Yes. And then, there were other really important results that were continuing along these directions by Nima and Rattazzi, and by Marcus Luthi and Rattazzi. So now then they did start, at that point, anomaly mediation was coming into the picture. So they did try to actually map the soft breaking masses through the duality. And so this is something that we are going to be continuing along this direction. But it turns out that they actually ignored, in their case, the pure anomaly mediating effect and the AMSB effects. And that's the one that will actually be playing the most important role in our results. Okay, so let me see just one more before I get to our results. So the most systematic one was by Zohar, Komargotsky, Steve Abel, and Matt Buchan about 10 years ago. So there, they just said, okay, so we really want the full mapping of, through dualities. So let's just, use the obvious objects, the conserved currents. So those will exactly be mapped through the duality. And then they were trying to relate all the supersymmetry breaking terms that you're adding in the UV theory, like some soft breaking parameters, to conserve currents, and then find the corresponding SUSY breaking terms in the IR theory. So this is, of course, completely correct, and there's absolutely nothing wrong with it. Yes, but they just didn't try to have a full complete set of supersymmetry breaking that would actually give you the right UV theory. So they, this mapping that they found is definitely correct, and our results are going to be in correspondence with that. Okay, very good. So yeah, so ideally we would like to have a full UV theory, yes, where you are actually completely in control of all the effects of supersymmetry breaking, yes, so that there is no additional, for example, if you just say I have an X spurion, yes, then you can map some of the parameters of the theory, yes, but you don't really know, is there another X dagger X times Q dagger Q? How does that exactly show up in the theory? Yes, so we would like to have a setup where really all the aspects of supersymmetry breaking are completely going to be mapped over from the UV to the IR theory. So because of that, we are trying to use really the simplest form of anomaly mediated supersymmetry breaking. So this was started by Hitoshi early this year, and the one thing I would like to emphasize is that, of course, when we talk about AMSB here, AMSB originally was sort of designed by Randall and Sandrum, and also by Hitoshi, Marcus, Rattazzi, and Gidice, to sort of get a UV completion of the standard model. So basically have a version of the MSSM where you have a predictive soft breaking pattern. Now, this is not how we are going to be using anomaly mediation. Yes, so we are not trying to build a BSM model like they did, where the standard model is an effective theory of a particular MSSM with some soft breaking. we are purely trying to use AMSB to just give the type of perturbation to Seiberg duality and Seiberg supersymmetric QCDs that will tell us what the phase of the slightly perturbed supersymmetric QCD is going to be. Okay, so we are again so that's how we are going to use AMSB. So it shouldn't be thought of now as a BSM model. Yes, so we are not trying to find what the soft breaking terms are for squarks and slaptons and all of that. Yes. So just to remind you, so anomaly mediation is a type of supersymmetry breaking where the mediation is happening purely by supergravity. There are no direct interactions between the SUSY sector and the matter sector. Okay, so again, this was the original proposal, and again, initially the way they were thinking about this is to build a BSM model. Yes, but that's not what we are trying to do. We are just trying to use this sort of purest form of supersymmetry breaking to see how to map the SUSY breaking effects from the electric to the magnetic theory. Okay, and so again, the assumption is that there is no direct interaction here. This is what was called sequestering, and the only source of supersymmetry breaking will be the auxiliary field of the supergravity multiplet.
But can I ask a question here? So that means now that you will have you're coupling to gravity, so you'll have the graviton now in the low energy spectrum.
So the nice thing is that like Pomerol and Rattazzi showed back in '99 that actually the best way to describe the effect of anomaly mediation is by just simply introducing this chiral compensator field. Okay, so this is called a Weil compensator or a chiral compensator, and the effects of supersymmetry breaking in the visible sector, or in the low energy effective theory, yes, are actually going to show up through the coupling of this chiral compensator to your Kähler potential and your superpotential, and that's it.
Oh, and that's it. So no gravity at this point.
There's no gravity left. So basically, this is completely UV insensitive. So the beauty of anomaly mediation is that what the effect of supersymmetry breaking is, you can completely specify within the effective theory, within the low energy effective theory, because it's anomaly mediation.
Yeah,
but coupled is it doesn't matter. So it's totally UV insensitive approach to.
No, but Csaba, this compensator, okay, whatever it was associated with gravity, no, I mean I mean it was needed to write gravity in the right way, right? I mean, but I'm wondering that in the way you're using it, it's kind of effectively it's a way to describe no, because a compensator would be expressed in terms of other fields, right? Effectively. So in this way, you can say that it is certain type of interaction between those fields. When you substitute this compensator, then no, maybe I'm not sure whether it would be local or whatever, but it would be certain, kind of effective interaction introduced, without even saying the word compensator.
So again, I'm not going to go through that derivation, but so this was the main result of Pomerol and Rattazzi, that really, all the anomaly AMSB effects, are just going to be completely UV insensitive. So it doesn't matter what happened at the high energies. As you integrate out fields, yes, all the effects of anomaly mediation are going to be summarized within the effective theory.
Yeah.
Right? And it's described, by this very simple coupling of your Kähler and superpotential to the chiral compensator.
No, but I wonder if you do it this way, then you can say that you kind of this phi field is a kind of notation for a certain combination of your other fields, right? Because you will
again. So you see, the M is basically a combination of the WAVs and the Planck scale, etc. Okay. Yes, this is the effective.
So it becomes just parameters, right?
Yes. but for us, these are just these, it's just going to be a single parameter that is going to be showing up in the.
But just
excuse me.
Go ahead, Misha. Go ahead, Misha. Go.
Yeah, excuse me, Csaba. So the power of this, what you call compensator, it looks like a dilaton field.
It's basically like a dilaton, exactly.
Yeah, the power is related to the real dimension of the corresponding field. Let's just phi cube here and phi there, phi bar.
Exactly, absolutely. The fact that you can fix the powers through ordinary power counting, basically, ordinary dimensionful power counting. So let me just show you like one example here. Yes, if the matter sector is conformal, yes, you can actually completely scale out the compensator from the theory. Yes, so you can actually rescale all the matter fields by the compensator. Yes, so for example, if you have a canonical Kähler potential and just the phi cube theory, yes, then actually you can just redefine your fields and there will be no effect of supersymmetry breaking. Okay.
Exactly. It's like with a dilaton.
Exactly. It is exactly like a dilaton. So the beauty is that all the effects of supersymmetry breaking will be tied to the violations of conformality. So they will be given either by just the naive counting of the dimensions or through RG running.
I see. Okay. So in this way, it would be soft breaking, right?
Exactly. Yes, absolutely soft. Yes, of course.
So then, because you mentioned before that you criticized the previous methods because they use this field X, right? So what's the difference between using this X and this phi field, right? It still is a spurion, right?
Well, it's still a spurion, but again, in this case, we know all the places where it's showing up. Yes.
I see. So you're basically using this conformal aspect
so the
of
fact
the
that we have this conformal counting, yes.
And the previous.
You actually know all the sources. I mean, by the way, I didn't want to criticize it. It's
no, I didn't mean it. I didn't mean it in a negative way. I'm just saying, but that was no, I just meant that that was the problem with the X field, right? You didn't know higher order.
You didn't know all the higher terms, and they may still be important. Yes.
Okay.
Basically, you didn't know all but here the beauty is that you know the Kähler term also.
Yeah. Okay. I see. Thanks. Yeah.
So then you can go ahead and for example, you can get all the effects that are induced from RG running. Yes. So the RG running is going to introduce a gaugino mass for you that is proportional to just the beta function of the gauge group, and then the soft scalar masses are going to be proportional to the anomalous dimensions of the theory, and there will also be A terms. So exactly. So like Arkady was asking, these will be the normal soft breaking terms that are generated, and they are going to be related to the RG running of the theory.
And what means mu in the
mu is a given scale here. Is the
but in the previous in the first line m lambda it's
at scale mu at RG scale mu.
Okay, so
it's a running lambda. Yes, it's a running.
But then on the right is the second power in mu, right, or what?
I'm sorry.
No, look at the right hand side. It's mu multiplied by m. What is it?
No. This is the beta function of I guess this mu should be maybe the fact that the gauge coupling is evaluated at scale mu. So this is not mu. This is not mu times m. Sorry. But this function evaluated at scale mu times m.
I see.
Okay. And so the real beauty of this is that if you now look at supersymmetric QCD on the electric theory, yes, and you calculate what the soft breaking terms are, that's what you're actually going to find is that as soon as the theory becomes anomaly free, the scalar masses for the quarks are going to become positive. Okay, and there's also a gaugino mass. Okay, so if you just take pure anomaly mediation on the electric theory, yes, it actually gives you exactly the kind of massless spectrum that you are interested in, which is the one corresponding to QCD. Yes, of course, we are assuming that supersymmetry breaking is small, so it's not quite QCD. Yes, it's a little bit of a stretch. Yes, it's the exact massless spectrum is QCD, and then we do have the squarks and the gauginos that picked up a little bit of a mass from anomaly mediation. But at least at the massless level, it is exactly the right spectrum, yes? And then here, of course, what I would like to also remind you that we don't have the kind of problems that AMSB had, where, you had like, negative slapped on mass squares, yes, because we are only looking at QCD. We are not trying to do the whole standard model. So we don't have like gauged U1 factors, etc. So every field is supposed to be, transforming under the non-abelian gauge symmetries. So all of these
I'm sorry, and M here is just a parameter, right?
So M is basically so we use it as a parameter. In the full theory, it would be a combination of M Planck and whatever the actual SUSY breaking scale was. But for us, it's just a parameter, yes.
But I think in the BSM models, it was the gravitino mass, right?
Yeah, exactly. So it's Okay, so what I wanted to say is that the loop-induced effects will give you a positive squark mass and the gaugino mass, and the massless spectrum is that of QCD, yes. And again, this is sort of a perfect UV boundary condition for trying to find, sort of the phase of the theory exactly. And we don't have this tachyonic problem here because they're only dealing with asymptotically free theories. Now, one thing that is sort of surprising, and I think this is the effect that really people haven't included previously, which is that, of course, there is also a scalar potential term generated from anomaly mediation if the superpotential is not exactly dimension 3. Okay. So there's an additional 3-level term. So this is not a loop-induced term. Yes. If the superpotential that is present is not exactly dimension 3, yes, then there will be a non-vanishing additional scalar potential in the theory that is derived from the superpotential. Okay. So if the superpotential is dimension 3, then of course this is vanishing, yes, but not in general. And you can actually check, what the expression is. If you have a general Kähler potential, we generalize this expression. So for more, so this is assuming a canonical Kähler potential. If the Kähler potential is not canonical, then the corresponding term is going to be given by that expression. Okay, so for example, okay, so here is the simple example that Hitoshi first found. If you look at now the ADS superpotential case, so the case when NF is less than NC, okay, so you do have a superpotential present in the theory that is not dimension 3, yes, because it has 1 over the fields showing up, yes. So then there will be an additional term that is going to be generated in the scalar potential in the theory, yes, and this phi is sort of a generic direction, yes. We are going to be assuming that it's a generic direction in the squark fields, where the meson is given by this phi squared. So there will be this additional term in the scalar potential generated, and so this is the key additional piece. So this is like a non-perturbative effect, sort of proportional to the original pieces in the ADS superpotential, yes, but also involves supersymmetry breaking. And the AMSB will allow you to pin down these particular terms. Again, formally it is 3-level, but of course it also includes non-perturbative effects and supersymmetry breaking. So it's not totally clear, what the real origin of this term is, but AMSB tells you that this has to be there. Okay, and
but in this case, let's take an F equivalent C minus 1, right, for example, yeah, and try to apply the same procedure, right? Then you will get your term.
That's what I'm doing, yes. So what will happen is that now, before the theory had a runaway vacuum, but if you add this additional piece that AMSB is forcing on you, that is the ADS superpotential combined with AMSB, it will actually find a stable minimum of this. It will stabilize the minimum of this of the theory at a non-runaway position without adding any quark masses to the theory. Okay? And the SUSY breaking pattern is going to be exactly sort of the right SUSY breaking, the global symmetry breaking pattern will be exactly the right one that you would expect in QCD, where the flavor symmetry SUF cross SUF is broken to the diagonal one, and the only massless degrees of freedom will just be the corresponding pions, like you would get in QCD. Okay?
But how much is different from the case when you regularize it with quark mass, right? No, like it was in supersymmetry, you know, because
if you have a quark mass, yes, you don't have a chiral symmetry anymore. Yes. So you don't, you can't talk about, truly chiral symmetry breaking, and you broke the chiral symmetry. Yes.
Yeah, I got it.
So here, it's really the dynamics that is doing the chiral symmetry breaking. So this one could be continuously connected to the actual QCD, yes, if you take supersymmetry breaking to be really, really large. Now, I don't claim that, that we have an evidence that, that there is no phase transition and that you truly can take this to be very large, beyond the fact that, the vacuum that you find is sort of the same vacuum that you think is going to be present in, is going to be the same that is present in ordinary QCD. Okay.
But why
can I ask a question about the
sorry. Why wouldn't this effect have been noticed by just adding squark masses, right? Because you could add squark masses and keep the fermions massless, and then you would have also had a symmetry breaking pattern like this.
Well, again, so there were some cases where people found similar symmetry breaking patterns, but it wasn't quite clear. Different people were claiming different things. In many cases they said there was still a runaway. I think they were. I would say, I talked with Zohar about it, and he also saw that this doesn't disagree at all with what he did. They just didn't quite found that, okay, so what is then the actual vacuum of the theory? Yes, they found a sum rule between the different soft breaking terms, and they didn't ask the question, okay, so then where will the theory actually settle to? Okay. And again, I would like to argue that this additional term, yes, so this I have not seen anywhere else written down. This, I mean, people know that it's there, but somehow they never used it for. They somehow assume that you start out at infinitely far out in the UV, and they go infinitely down to the IR, and they only looked at the RG running. Okay, so they ignored this finite effect. Okay, so let me. I'm really running out of time, and I'm just getting to the things that we were doing recently. At least let me tell you a few of those highlights. So we try to apply this to chiral gauge theories, and that's actually the hardest to do, yes, as I mentioned, because there's currently no reliable lattice results yet. Now, in the 70s, late 70s, early 80s, there was a proposal on how to deal with chiral gauge theories. So that was a proposal of Savas and I think Stuart Raby and maybe Susskind. They called it Tumbling, and what they said is, okay, let's postulate some fermion bilinears in a particular channel, which they call the most attractive channel, and say that that fermion bilinear is going to form a condensate, which will then break the gauge group, and it will reduce the gauge group. And they said, let's apply this until we get to a QCD-like theory. So let's keep breaking the gauge group with fermionic condensates until I reach a point where it becomes QCD-like, and then I will know what happens in the QCD-like theory. So that's sort of a it's like I said, it's like a cookbook prescription, yes. And they call it tumbling in the sense that you generate more and more condensates, and then at some point you're ending up at the QCD-like theory. Okay, so one of the most famous examples of this would be SUN with an antisymmetric, with a fermion in an antisymmetric representation, and N-4 antifundamentals. So you can check that this is designed such that the gauge anomalies are actually canceling. And then actually what tumbling would tell you is that you start out with this condensate between the antisymmetric and the anti-fundamental that will break the SUN gauge group and the SUN-4 global symmetry down to an SUN-4 diagonal subgroup of the gauge and the global symmetry, and an SU4 global gauge symmetry left. Okay, so the original gauge times global will be broken to a much smaller gauge symmetry, SU4, and an SUN-4 global symmetry. So SU4 would be the remaining gauge QCD-like gauge symmetry, yes, because in SU4 the antisymmetric is already non-chiral, because in SU4 the antisymmetric and the conjugate antisymmetric is the same. And then, you know, they would say that, okay, this remaining SU4 is confining, that's QCD-like, so you are going to be left over with a theory with an SUN-4 global symmetry, which is actually, you know, really, you know, it's a combination of the original gauge and global symmetry. And because you had you have a leftover chiral symmetry that is unbroken, yes, there's a Tuft anomaly that you have to match. And they checked that this composite, where you take the it's like a baryon-like composite, where you take 3 fermions, 1 from the antisymmetric and 2 from the anti-fundamentals, that this combination, this bound state, is actually exactly matching the Tuft anomalies of this SUN-4 global symmetry. Okay, so this is one of the most well-known. So if you look at SU5 case, and you look at, for example, the supersymmetric version of this. So if you take SU5 with an antisymmetric and an anti-fundamental, this is one of the most famous SUSY gauge theories. And, you know, people call this the mother of all SUSY breaking theories. It's one of those very few theories where there's actually no flat direction at all. So you have one antisymmetric and one anti-fundamental, specifically for the case of SU5. There's no flat direction at all. And there's an anomaly-free R symmetry. And you can argue actually pretty convincingly that in this case, the expectation is that supersymmetry is dynamically broken. So it's already the supersymmetric theory without adding anomaly mediation or anything is one of those theories that will break supersymmetry dynamically, but it's uncalculable. Okay, so this was one of the first examples early on in the 80s. I think it was also Affleck-Dine and Seiberg who looked at this theory and talked about this as the first example of dynamical supersymmetry breaking. Now, later on, people realized that if you add an extra flavor or more than one flavor to the theory, then it actually can become calculable. Yes, so in the presence of an extra flavor, this SU5 theory will be calculable and still break supersymmetry dynamically. Now, the interesting thing is that, you know, people have been looking at this theory since, again, the early 80s. And there's one thing that everybody sort of, you know, neglected to mention. So we call this a new observation, but I put it in parentheses because I'm not 100% sure. Just the fact that we didn't see it mentioning anywhere doesn't mean that people really didn't know it. But it looks like, you know, there's an additional unbroken U1 symmetry in the actual vacuum of the theory. And I'm still talking about the fully supersymmetric theory that is dynamically broken. Okay, so you can go ahead and, for example, add an extra flavor and analyze this theory. And you can see that there is actually this U1 global symmetry that if you look at what the minimum of where the minimum of the theory is going to lie, you know, this symmetry is actually going to be unbroken completely. Okay, so there's an unbroken U1 in this theory. Okay, and again, you know, we went through. I don't want to go through all the details. We added the extra flavor. We did the analysis of the theory, and we found that indeed, you know, it is supersymmetry is dynamically broken, and there will be a massless fermion that will be there to match the Tuft anomalies for the remaining U1 symmetry. Yes, so this U1 symmetry is the one that people didn't know about, and we claim that has to be there. Yes, and so for example, when Affleck-Dine and Seiberg, you know, looked at this dynamical supersymmetry breaking, they never said that actually there's got to be a massless fermion in this theory, yes, in the SUSY breaking, because nobody knew that this extra U1 is actually there. Okay, so it will be unbroken, and then there is a composite fermion that matches the anomalies. And this is in addition to the Goldstino, yes. The Goldstino is there because supersymmetry is dynamically broken, but that doesn't carry any global charges. So that couldn't possibly be the fermion that is matching the 't Hooft anomalies for this extra U1. Now, what happens if I...
So this anomaly, sorry, this symmetry is anomaly. It's not anomalous.
It's a global symmetry. It's a global symmetry. So it has anomaly-free global symmetry that has 't Hooft anomalies. Yes. So the U1 cube, yes, that's non-zero.
Yeah, that's non-zero. Okay.
U1 cube is non-zero, but it's anomaly-free. So
yeah, okay.
Under the gauge symmetries, yes. Now, what happens if you add anomaly mediation? So if you add directly on top of, so this is a theory that breaks supersymmetry dynamically, yes, but it's I'm asking now what happens in the non-supersymmetric version of this theory. So I'm adding anomaly mediation on top of this. Now, when I add a little bit of anomaly mediation, you don't expect the fact that there's dynamical supersymmetry breaking to change very much, because you get a vacuum that is proportional to the dynamical scale of the theory, and you are perturbing it with a little bit of supersymmetry breaking. However, the Goldstino will pick up a mass, yes, because now I have an explicit source of SUSY breaking. But the fact that I have this unbroken global symmetry, that remains there. Okay, so the fermion that had to be there because you had because you had this unbroken U1 symmetry, that actually has to be there. So now, if you check,
you mean U15 stays unbroken after this?
Stays unbroken, yes, right. U15 stays unbroken, yes. So in the tumbling picture, the non-supersymmetric version of SU5, yes. So the expectation would be that the SU5 is broken down to SU4 through this condensate of two antisymmetrics, because that would be the most attractive channel. And then you can decompose your antisymmetric under SU4. So it's going to give you a 6, which is now chiral. Is non-chiral, is vector-like. And then the 4 and the 4 bar, yes, those are also non-chiral vector-like, yes. So the expectation is that once you have this condensate, then the vector-like piece is condensed, but this 1 minus 5 will remain. So in fact, the tumbling picture also tells you that that there should be an extra massless fermion present in the theory. Okay, let's see. And so that's nice. Okay, very good. So now we also did the case for the general SUN, both for even and odd, and okay, I'm really running out of time. So let me just do this, and then I'll do the, maybe then, we can thank, and then whoever wants to listen to.
Yeah, it's okay if you need a little bit more time. It's
okay.
fine. Yeah.
Okay, let me try to say a few more. Okay, so we did, for the antisymmetric case, we did the general case as well. And it turns out that here, you actually had to make a distinction whether n was even or n was odd. Okay, so first we looked at the case when n was odd, so SUN is odd, and in this case, when you have the supersymmetric limit, there is actually a flat direction. Yes, so that's different than for SU5. So there is a flat direction here, but in this flat direction, so you have an antisymmetric, the antisymmetric tensor n-5 components of those are turned on, and that's actually going to be compensated. I mean, they're after they're in the d-flatness direction. It's going to be compensated by turning on some VAFs for the squarks. Okay, and along this flat direction, the SUN gauge times SUN minus 4 global is going to be broken to SU5. You see, there's this SU5 component down here. So that's the same kind of SU5 that we see in the case with lower n. Yes, and then the flavor symmetry is broken to SPN minus 5, because and then there's a U1. Okay, and the SP is due to the fact that along this flat direction, yes, the composite A F bar picks up an antisymmetric VAV. Yeah, so the antisymmetric VAV always breaks the flavor symmetries, SUN flavor symmetry down to SP. Okay, and so what you are left over with now is an SU5 theory like you had before. Yes. And that one is supposed to break the gauge symmetry, the supersymmetry dynamically, and it will give you a potential term, not a superpotential term, a potential term. That's just due to the fact that it broke supersymmetry dynamically, which is lambda to the force. Yes, something of the order of lambda to the force of the low energy effective theory. But of course, the lambda of the low energy effective theory depends on the fields, on the VAVs of the high energy theory, how far out you went on the flat directions. Yes, so you would get again this runaway type potential. So on its own, you know, this theory would be valid without any perturbations. Now, in the supersymmetric case, you can actually stabilize this runaway by adding a 3-level superpotential. With AMSB, no stabilization is needed because you will have the loop-induced SUSY breaking effects that will actually stabilize your vacuum, and you will get a stable ground state in the theory along this direction at a large VAV. Okay, so at a VAV that is much larger than the dynamical scale of the theory. So there is a, you know, so what AMSB would tell you is that the symmetry breaking pattern is SUN minus 4 cross U1 broken to SP n minus 5 cross U1.
Yeah, but I saw that you are taking M much larger than lambda, or it's not in this case.
So we of course, you know, where our methods are reliable is when M is really small. Yes, that's when our methods are reliable. I see. Now, of course, eventually, I would hope that there's some miracle happening, yes, and maybe I could take M very large, yes, but I don't really have any, you know, any good arguments that I could do that. So my actual analysis is always in the limit when M is very small compared to lambda. Yes, that's when my methods are reliable. Okay.
Does that mean,
yes.
Does that mean you always have a Goldstino in your spectrum, right?
Well, you know, I mean, from the point of view of this theory, as the Goldstino, this is an explicit breaking of supersymmetry from the point of view of this effective theory. So I don't have a Goldstino. Yes, the Goldstino is probably, you know, somewhere in the Sugra sector. Or,
But is the Goldstino sitting inside the phi field, the compensator field phi? Is that where its origin is, or is it even further in the UV theory?
Yeah, I think it's further up. Yes.
Okay.
And probably, you know, I mean, the point is that, you know, the scale of supersymmetry breaking here is compared to what it is in the high theory is very small. So probably truly would be a linear combination of the two. Yes, but the assumption is that it's purely living there. And what I want to emphasize here is that so I get a global symmetry breaking pattern that is different than what Tumbling is predicting for you. So I get here SUN minus 4 cross U1 broken to SPN minus 5 cross U1. And Tumbling would tell you, as I told you, that the global symmetry is unbroken completely. Okay, so here, using our methods, I get sort of a different prediction for what we think possibly the symmetry breaking pattern and the actual vacuum of the non-supersymmetric version of this SUN with an antisymmetric tensor would be. Of course, you know, we don't really have an argument that this will be maintained when, like Arkady was saying, you know, when I take M much larger than lambda, yes, there could be a phase transition, yes. But what I'm trying to say is that, you know, this is a consistent phase on its own. Yes, it could be, there doesn't have to be a phase transition. Yes, so this is another candidate phase for the chiral theory. Yes, and again, you know, the arguments in the Tumbling are pretty weak. In fact, we could go back to the Tumbling and ask, could we make the Tumbling actually consistent with our vacuum? Yes, and in fact, it turns out that that the answer is yes. If you just take the most attractive channel, then you will get the breaking where the full global symmetry is unbroken. But if you look at the second most attractive channel and assume that there is that is not only one condensate, as the Tumbling people's cookbook was saying, but there's a second one, that's nothing that would forbid that, yes? Then in fact, you would break your SUN-4 global symmetry to SPN-5. Okay, so again, it's basically just saying that, we think that it's very plausible that the correct symmetry breaking pattern of these chiral theories is not what the most naive expectation is, but probably there is a second condensate there, and this is something that once the lattice people really are able to do the simulations of the chiral theories, they could check, yes, they could then find, okay, so what is the true vacuum structure of the theory? Yes, certainly in the supersymmetric theory with the small perturbation, it's definitely what we are saying. Yes, now it's also, you can check that this phase is consistent with having no phase transition, in the sense that the vacuum does not contain any massless degrees of freedom that wouldn't have a corresponding field in the limit when you take supersymmetry breaking to infinity. Yes. Sometimes, in some of the problems, for example, with the phases that Cinchia and Yael found, was that they found a phase that, okay, it seemed to make sense, but they had some massless degrees of freedom that contained, for example, the squarks. Yes. Now, if you find some massless degrees of freedom that contain the squarks, you really don't expect those degrees of freedom to remain massless when you take supersymmetry breaking to infinity. Yes. Because then the constituent mass itself will be very, very large. Yes, they could be massless when the constituent mass is very small compared to the dynamical scale, but it's very unlikely to remain massless when you take SUSY breaking to infinity. Yes, now we don't have any of those. So for anything that had to remain massless, there was a corresponding interpolating field in the pure non-supersymmetric theory. So that's something that what I mean by that there's no obvious signal for there having to have a phase transition occurring as you take the supersymmetry breaking to be very large. Of course, that's also not a proof that there is no phase transition, yes, but there's nothing that forces you. So it could be continuously connected possibly to a phase of the non-supersymmetric theory. That's the strongest statement that I can make. Okay, so let me so we did the same for the even N, and there we found another slightly different global symmetry breaking pattern. So there, instead of SUN-4, you've got SPN-4, okay, whatever. So, and then we did the case with the symmetric tensor. So that was quite different in terms of the analysis, because there, instead of having all of these SUSY breaking theories, you actually had to go to one of these magnetic duels that was found by Pouliot and Strassler. So that's, these are one of the most miraculous dualities, I would say, because really, okay, the SUSY QCD dualities you can guess, but this duality where you have an SUN-4 with a symmetric and some flavors, I think, the fact that they found this one, that's pretty amazing. So that's one of those few cases that actually has a dual, and it's one of those very weird ones where the dual theory is non-chiral. If you remember, they had these chiral duals of non-chiral theories or non-chiral duals. So the original theory is chiral, obviously, yes. It's the symmetric tensor in it, and the dual is non-chiral. Okay, but there's nothing that tells you that this has that whether or not the theory is chiral has to be an invariant notion. Okay, so we analyzed this, and then we found what the right symmetry breaking pattern for this theory is. And again, it's a slightly different type of analysis, but again, we found that the symmetry breaking pattern is different than what you would get for from Tumbling, and we are able to. So here, we would get SUN broken to SO. Okay, very good. And then we had another whole big enterprise, which was the analysis of the SON theories. And the only thing I want to say is, this was a lot of fun, and we learned a lot about this. Now, the really nice thing about the SO theories is why it's useful to look at this versus the QCD, just the SUN, because this theory could possibly be truly confining in the sense of, when you have a vector of SON, yes, that's actually not the smallest representation. It's not there will be a center left over for the gauge group. So in fact, a vector cannot screen all possible external test charges. So this theory could possibly be actually confining. And indeed, if you go through the phases, there's one particular really nice case where the Seiberg dual type description actually, so this is Intriligator and Seiberg who did this, who actually, where you actually have a massless monopole showing up. Okay, so that's the case when you have SO with n-2 vectors. And it's clear why it should be that case, because when you have n-2 vectors, you break SON to SO2, which is just a U1 theory. And so that's a Tuft-Polyakov-like theory, yes, where you have a U1 left over, a pure U1 left over. So this is where you expect monopoles to play a role. And indeed, in this case, there are monopoles and they do become massless. And there's a Seiberg-Witten-like description for at least, the dynamics of these monopoles. And what we were able to show is that if you add anomaly mediation to this particular case, yes, then you actually will make the monopoles condense. And so you will get a monopole condensation. And that is actually what is going to be the dynamics for confinement in these theories. Okay, so it's sort of similar to what Seiberg and Witten did for perturbing n equals 2 to n equals 1. Now we are perturbing the n equals 1 theory to n equals 0, and we are finding that those monopoles indeed are going to be confining, condensing, which
it would be Csaba, it would be confining, kind of this U1 confining in similar way as Seiberg-Witten.
Exactly, that's what I'm saying. It's like Seiberg-Witten, yes, when they showed from going from n equals 2 to n equals 1. Yeah. Yes, it's sort of the analog of that.
Yeah.
For the SO theory, and it wasn't totally trivial because there were two different kind of singularities, and you had to check which one has the lower minimum. So it was a lot of fun. So I would like to ask you, if you're interested, to just look at the paper and go through this. And I'm just gonna conclude. One more thing, yes, that. So then if you go to lower number of flavors below Fn-2, you can still show that the dynamics of confinement in those theories is still going to be monopole condensation. Okay, so that's, and we did all of the phases for SO. And again, what we actually find is that basically in every single case, it's going to be confinement plus chiral symmetry breaking, except there could be a conformal phase. So again, it's very, very much like what you're expecting in QCD. You see in supersymmetry, there are this really large number of possibilities that Intriligator and Seiberg worked out. It was a lot of work for them to find all the special cases. And when we add AMSB, we basically just find just one particular pattern of confinement and chiral symmetry breaking, yes. So SUF broken to SOF, or maybe a conformal phase. So it's exactly the kind of thing that we are expecting, from our experience with ordinary QCD, that there are only two kinds of phases. Everything from supersymmetry, all these special cases are going to collapse to just the two basic cases. Okay. So again, of course, the big question is what happens when M is much bigger than lambda? Yes. So our results, I think, are pretty clean when M is smaller than lambda, but and already, I think our results are pretty interesting in that case on its own. So I don't think I should apologize for anything. But of course, the most interesting case would be to understand what happens when SUSY breaking is super large. Yes, there may be a phase transition. Now we have in all our results, we see no reason why there has to be a phase transition. So as I said, all of them can be connected to the expected phases of the non-supersymmetric theories. Now, this is, of course, not a proof that there is no phase transition, yes. Now, can holomorphy help? Okay. So, I mean, you can try to cook up arguments where you say, well, this is coming from the web of a chiral superfield, this chiral compensator, this conformal compensator is a chiral superfield, and the phase transition must be described, if there is one, it's got to be in the vicinity when M, the supersymmetry breaking scale, is of the order of lambda, but there is no holomorphic way to get sort of, a true phase boundary that would correspond to a phase transition of this sort. Okay. Are there loopholes here? Probably. So,
but
you're taking this very seriously. But we are hoping that somebody out of you will take this more seriously and see if this makes sense.
Csaba, but you mentioned before that M could have a meaning. I don't know, like gravitational mass or whatever. So it has some physical meaning, right? What you are saying. When M is much lower than lambda, doesn't imply certain dynamical field with lower mass.
So that's a good question. Yes. So if I take M to be really, really large, yes, would I have to then now take the dynamics of the full theory into account? Yes. So that may be a problem. Yes. So again, we are sort of saying that this came from another sector. Yes, but we can completely decouple the other sector and just look at the sector. Maybe then that breaks down. So.
But look, M is a mass in this other sector, and if you are saying that the other sector contains a slow mass, then it should be visible in certain sense. No,
sorry, no. So M is a combination of parameters from the other sector. Yes, it's
right. But I am trying to find out if there is a kind of direct physical interpretation of this mass that would, if it would be mass of say this gravitational field, then you would say that gravitational is light, right?
Right. Yeah.
No, that's why I'm asking. Yeah.
Right, but you can probably think of some limit when M Planck goes to infinity, but SUSY breaking also goes to infinity. But then I don't know. So, but yeah. So, I mean, all of these. So, I'm not claiming that we have an argument. I think it's something that is worth to think about, since our experience shows that whenever we try to apply it, we are finding sort of sensible results. By sensible, I mean results that you would expect from the non-supersymmetric theories. But again, it's still up in the air. All right, so I abused your time already. So what we were trying to do is use perturbations of supersymmetric exact results to find the vacuum structure of the non-supersymmetric gauge theories. This anomaly mediation appears to be a pretty good or superior method for perturbing the SUSY theories compared to what has been done before. It's completely insensitive. It's very predictive, and again, gives results that can be connected to the non-supersymmetric phases or the expected form of the non-supersymmetric phases of these theories. What I can say for sure is we found novel symmetry breaking patterns for the chiral gauge theories, both for the antisymmetric and the symmetric case, and we were able to establish confinement and chiral symmetry breaking in the SON cases via monopole condensation. All right, thank you very much.
Okay, well, thank you very much for the nice seminar. Thank you.
Csaba, the first part of your talk, is it already published in some form or on archive or something?
The chiral gauge theories?
The chiral gauge theories.
Yeah. We have the SU5 and the SUN with antisymmetric and the SUN with the symmetric. We have two papers on that, yes. One with the antisymmetric and the other is for the symmetric.
Okay, thank you.
Can I ask a question about the sort of big picture here?
Right.
So you opened by reminding us of the open problem of finding the lower edge of the conformal window in QCD.
Right.
And then you told us about an interesting sort of SUSY theories, where you can turn on small amounts of SUSY breaking and see where the lower edge of the conformal window is in those theories with a small amount of SUSY breaking, if I understand correctly.
Right.
Is that right?
So
would you say that that's then that gives you a prediction for where the lower edge of the conformal window is in QCD, or is it more like an estimate?
Well, that's a good question. You know, again, it depends on, you know, if there's a phase transition or not. Yes. So, I mean, it certainly gives you a prediction, but, you know, it's modulo this question of, you know, is there a phase transition or not? You know, I mean, if it could be that for certain number of flavors, there is a phase transition, and for certain number.
I mean, I have to say that seems like a very natural possibility, right? Because you have if you think about it,
possible, yes.
Yeah, I mean, QCD for like random values of NF has at least two possibilities for the ground state, which is consistent with anomalies. One is CFT, one is chiral symmetry breaking.
Right.
And you know, which one it chooses, if you had to put it, which one it chooses could easily be affected by adding some extra stuff, which is relatively light but not massless, right? So that pushes it towards one fixed point or the other.
So again, you know, what we are saying is we should be able to do this for the case when we add small perturbations.
Right, exactly.
That one is a prediction, yes.
That's a prediction. I agree completely. Yes.
So now for the case with the you know, the large SUSY breaking, of course, you know, I mean, I would love, you know, that's a prediction I would really like, yes. But I mean, right now we can make up stories like this, but again,
but within your approach, I think it still looks like a prediction, if you will accept your procedure.
It's a prediction for the theory with, you know, where you do have light quarks in the UV, yes. It's a prediction for those theories. It's QCD plus light quarks plus light gauginos. We have a prediction, yes. But, you know, then if I take those quarks to be completely out, yes.
So what's the consensus? And people have looked for lower edge of the conformal window on the lattice quite intensively over the last few years. What's the current consensus for the lower edge for NC equals 3?
As far as I understand, actually, you know, as far as I understand that it's actually 3 NC, F is greater than 3 NC, which would tell you that in the supersymmetric case, you shouldn't see any conformal theory at all. And actually, you know, we are still, you know, you may have seen that I was evading a little bit, you know, the discussion of the conformal window, because we are not, you know, we are still going back and forth, you know. In Hitoshi's original paper, he thought that there is a very large conformal window, but then he wrote another paper recently where he thinks that there isn't a conformal window at all within this, which would be in agreement with the lattice. So, you know, I'm hedging my bets on that. So I didn't give you a particular number because of that.
I see. Thank you.
How to properly analyze these theories, you know, the RGs in this theory, we are still, you know.
I'm sorry, I didn't understand. Let's assume that the lower edge of the conformal theory is at 3n, which is at n equal 3 is 9. It's still lower than the Bank-Zanks point, significantly lower. So why there is
so there's no contradiction with that one, absolutely. So in the non-supersymmetric case, yes.
Yes.
But for the supersymmetric one, that would be the edge, yes. That's where the supersymmetric theory has the Bank-Zanks fixed point.
No, but when in supersymmetric theory, we have both electric and magnetic. So when electric field becomes far away from this upper edge, you go to the magnetic theory and see what happens. You are close to the lower edge in the magnetic theory. So combining electric and magnetic, you know the upper edge and the lower edge. So there is a conformal window.
No, I see.
It's from 3n over. It's between 3n over 2 and 3n.
Okay. No, you're right. Okay. I never thought of. You're right. I never thought of applying the duality. You know, once you're below above f greater than 3n, because I assume, I know that it's, that it's IR free, yes. But I think you're right, yes.
Okay, Csaba, thank you very much. Unfortunately, my time has run out. I have to leave. But thank you. I will look into your publications.
Great, thanks.
Okay, so if there's no other questions, then we can officially stop the recording at this point, but I don't know if we can stop it. But anyway.